Hi everybody, welcome to this video about rivers and flooding. So we all know that floods are extremely destructive. One of the ones that stands out in our minds here in Vermont is the 2011 Hurricane Irene flood, which destroyed a lot of roads and reshaped a lot of river channels in Vermont. Did a profound amount of damage to rivers here and raised a lot of questions about how we manage our rivers and how we should be protecting our infrastructure from floods, especially in the face of intensifying floods as a result of climate change. So floods are destructive. Of course, they're also expensive. Irene damage in Vermont may have approached $570 million in damage. The state paid out roughly $100 million of that, and the feds picked up the rest. The feds being the Federal Emergency Management Agency, or FEMA, which of course is supported through our tax dollars. So when you wonder why we should be studying floods and trying to understand them, one answer is that you as a taxpayer are the one that pays for them when they damage infrastructure. So in this video, we're going to introduce the idea of river channels and floodplains. Then we're going to talk about flood hydrographs. Then we'll move on to kind of looking at some of the factors that control the intensity of flooding. And then we'll look at the idea of flood recurrence intervals, or how we're able to kind of predict roughly how often floods of a certain size occur. So a couple pieces of vocabulary. Floods occur when water in a river spills out of the main channel and onto the floodplain. Okay? The main channel is usually defined as this area between the steep banks, and beyond those steep banks is the floodplain, which is a low-lying flat area immediately adjacent to the main channel. And so of course, periodically during floods, waters spill out of the channel and they inundate the floodplain. Here's an example of that in the Mississippi River 2008 flood in Missouri. The main channel is out here, and you can see that the floodwaters have completely overtopped that channel and have inundated this entire area of the floodplain. So floodplain is kind of a relative term. It depends how bad the flood is. In a very large flood, everything gets included in the floodplain. In smaller floods, the water might only cover a more proximal piece of the floodplain. So how are floodplains built and how do they evolve over time? Well, the main way that they're built is actually by sedimentation. So that would be the settling out of fine silts and clays from floodwaters, which are actually relatively stagnant once they go over bank. So here's an example of flooding on the Pike River in Australia, and you can see that a lot of these areas of the floodplain are inundated, and in many cases they act almost as little lakes, temporary lakes, where the water's not really flowing very fast, it's very calm, and so silt and clay can settle out onto the floodplain. And of course, that causes the floodplain to grow upwards. So floodplains aggrade upwards by subsequent floods that are basically depositing more and more sediment on top of itself. So this soil pit shows a nice stratigraphy through some floodplain sediments. And we see it's made mostly of kind of homogeneous overbank muds with a little bit of sand and silt in there as well. But this is probably deposited in many different flood events that went out over the floodplain. So now let's look at a flood hydrograph. How do we kind of measure the intensity of a flood? And flood intensity, of course, is measured relative to the discharge in the river. Just to remind you, discharge is the amount of water flowing down a river. So it's a volume per time coming down the river channel. Okay? And we express discharge usually in the function of a graph called a hydrograph. And the x-axis here is time, and the y-axis is discharge, or the volume of water per time coming down the river. So this idealized hydrograph shows the floodwaters rising for the first few days, then a peak, and then the floodwaters falling off. And we call this the rising limb of the hydrograph and the falling limb of the hydrograph. So how do we actually measure discharge? In other words, how do we actually make a hydrograph? Well, the USGS and other scientists are maintaining networks of gauging stations where they actually measure the discharge of rivers directly. And the way that works is they pick a section of river with a relatively uniform and simple geometry. They install a measurement device that measures the pressure difference as the water level gets higher or lower. So they basically just measure the water level using this device, and that's actually called the stage. And then they've previously determined how both the velocity and the cross-sectional area relate to stage. So they know that relationship between stage, velocity, and area, and then just by measuring the stage, they can actually compute the discharge in real time and actually broadcast that information back to a central computer. So you can go online and get information about discharge in real time. And here's an example from the New Haven River in Vermont, which flows through Bristol, Vermont. And this is the hydrograph time series from the day of Hurricane Irene, or the week of Hurricane Irene. So take a look at this. Here's the stage, or the water level. It's sitting at about 3 feet on the Sunday before Irene. Within about 12 hours, it rises 10 feet. Imagine that. Literally a flash flood, 10-foot rise. And of course, that 10-foot rise translates to about 300 times increase in discharge. So keep in mind, even though the height of the river only rises by about a factor of 4, because the channel area is getting much larger as the water rises, the discharge increases even faster. So there's not a linear relationship between stage and discharge. It's a non-linear relationship. So now that we know how a hydrograph is measured, let's look a little bit about how the discharge of a flood might change in the downstream direction. In other words, how does that river kind of move downstream? How does a flood coalesce to become more or less severe? So obviously all floods start with really intense rainfall, of course, but there's also opportunities for that floodwater to be mitigated as it flows down a river. And specifically, floodplains can act as temporary storage reservoirs that buffer downstream flow. In other words, a lot of water can get stored on the floodplain, and it's temporary storage, but what it means is that that water doesn't go immediately downstream and start making the flooding downstream worse. So an example of that is here, floodplains of the Mississippi River during the 2008 flood. So keep in mind the scale here. This is Kentucky, Tennessee, Arkansas. Looks like 20-kilometer scale bars. This is a big scale. And notice before the flood and then after or during the flood, huge areas of floodplain are covered in water. So there's just vast amounts of water being stored in these floodplains. And that means it's not moving directly downstream. So let's just illustrate that one other way. Imagine you have just a simple shallow river channel and you send some floodwaters down it. That river channel is going to fill up really quickly and then just continue to pass that water right downstream. A floodplain, in contrast, can act more like a big bathtub. It takes a while of inflow in order to fill up that floodplain. You can store a lot of water in there until eventually it's full and it starts to pass that water downstream, but not before it's acted as a major buffer. So what's the effect of this? Well, the effect of this is it actually delays flood crests. It actually puts in a lag between the time when floods hit different places. So back to this 2008 flood on the Mississippi River, the high point or the crest of the flood hits New Madrid, Missouri on May 7th, okay? Doesn't hit New Orleans until 2 weeks later on May 24th. So it takes 2 weeks for the peak in flooding to reach all the way down to New Orleans. And the reason, of course, is because as the water's making its way down, it first has to fill up all this floodplain area before it can start really passing a lot of water further downstream. So it takes time to fill up all these floodplains, which delays the crest of the flood and acts as a really important buffer on flood intensity. Now, a very similar example happened in Hurricane Irene in Vermont. It turns out that Middlebury, Vermont, is protected by a lot of upstream floodplain area. Specifically, if you've ever gone south of Middlebury, there's an extensive area of low elevation swamps called the Cornwall Swamp or the Cornwall floodplain. And this kind of swampy area extends all the way down to Rutland. So even though the Irene floodwaters were raging out of the mountain streams, a lot of that water was being temporarily stored in these floodplains and was acting to delay and diminish the peak of the floodwaters in Middlebury. So for example, a lot of the Irene destruction happened on a Sunday afternoon, and the floodwaters in Middlebury didn't peak until 5 days later on a Friday afternoon. And here's what that looked like. The water was high, it was raging over the falls, but it actually never really went over bank in Middlebury. So the town was not damaged at all. Now, it's important to note that a lot of these ideas we've just talked about are focused on what we would call lowland channels that have very large floodplains, like the Mississippi River. Many rivers exist, of course, in mountain channels, smaller rivers that are confined in really narrow valleys. So these mountain rivers don't have large floodplains. And as a result, mountain rivers are much more vulnerable to flash flooding. There's nowhere for that water to go to be stored, so it just immediately inundates the whole valley and can be very, very destructive. And of course, this is where a lot of the damage from Irene happened, was up in the small mountain valleys that didn't have any floodplain buffering. Okay, so we've talked a little bit about the hydrograph and how floodplains can control the intensity of flooding. Let's look at a couple other factors that also control the intensity of flooding. And of course, a big one brings us right back to floodplains. It's common in engineering and farming that we want to disconnect rivers from their floodplain. In many cases, this would be because farmers want to farm the very arable floodplain soils. So they might erect a levee that's intended as a wall to keep the floodwaters out off their fields. And what that does is that really disconnects the floodplain from the channel and takes away that storage space. So if you take away that storage space, that means the downstream flooding is going to be even more intense, and it's going to happen faster because you can't store that water. And there's a lot of other examples of disconnection from floodplains as well, not just levees, but road embankments and other man-made structures that tend to do this. So that's the first factor that makes flooding more intense. A second factor that makes flooding more intense is actually the intensity of the rainstorm or the precipitation rate. Obviously, flooding is driven by precipitation. So if we get really intense storms, more of that water runs off and we get more violent flooding. And of course, given that global warming is accelerating, one of the results of that is going to be more frequent large storms. And this plot illustrates that. It shows the average number of named tropical storms in the North Atlantic over the last 70, 80 years. And we see a marked increase over the last 10 to 15 years, potentially due to the effects of warming climate, more energy available to drum up these storms. But of course, in terms of flooding, this translates to more severe flooding. So a third factor that influences the intensity of flooding is surface permeability and the runoff fraction. So permeability refers to the ability of a soil to transmit water, and some soils, like forest soils, tend to be very permeable. They have a lot of organic material, a lot of pore space, so water can absorb into these soils very quickly, and it does not run off. In contrast, impermeable parking lots and other built-up areas do not absorb water at all. They are impermeable. That water immediately runs off into the river. So impermeable surfaces would have a higher fraction of runoff than permeable. And of course, that's going to result in much more intense floods. And just another look at that, this plays out at the landscape scale as well. So you could think of some watersheds as being very permeable, having low runoff fraction, other watersheds as being very impermeable, like New York City. And that's really one of the take-home messages here, is that urban environments tend to promote more rapid and more intense flooding. They're covered with impermeable surfaces, like we just talked about, but also they are designed to drain water out of the urban region as quickly as possible. So we have things like storm drains and storm sewers, as well as canals. All these features are designed to quickly and efficiently drain water off of the impermeable surfaces. The problem is that water then goes immediately into the river system, much faster than it would have, and that builds up much more intense flooding. So if we look at the difference between a landscape that has 90 to 100% runoff, like an urban one, versus maybe a forested landscape, we tend to see much flashier floods in the urban environment because that water runs off immediately and it all runs off, okay? So what do I mean by flashier? I mean the rising limb is steeper, and then the declining limb is also steeper. So there's a lower lag time here, and that flood builds very, very quickly. Now, of course, the other result is that the peak flow is actually much larger as well. Basically, the water's flushing through the system faster, so it actually peaks higher than if you had spread that flow out over a longer time period. Okay? So, in summary, building up impermeable surfaces in urban areas gives us flashier floods and also gives us bigger floods. And just a reminder, that's important business. Even a couple meters of extra height during a flood event can translate to a huge amount of extra inundation. So imagine this was the height of the floodwaters without urbanization, but then the urbanization causes just a couple meters higher. Well, that could be the difference between no damage and between inundating an entire area. So anything we can do to keep the intensity of these peak flood discharges lower is really, really valuable. So I just want to wind up this lecture with the idea of flood recurrence intervals. So what is a flood recurrence interval? Well, it's the average time between floods of a given discharge. So what does that mean? That means that if you have a certain discharge, okay, like let's say 47,000 cubic feet per second, okay, for that given discharge, on average, it occurs every 10 years, okay? So that's the 10-year flood. Now, a bit bigger flood, like 60,000 cubic feet per second, on average, that would occur every 40 years. So obviously the relationship here is the bigger the flood event, the more rare it is, okay? Now, a couple things. This is obviously a statistical measure, okay? This doesn't mean a 60,000 CFS flood occurs exactly every 40 years. It just means, on average, that's about the recurrence interval of that size flood. And it's important to understand also how these metrics are estimated. The way it's done is that hydrologists gather data on historical floods, and that's usually over human timescales. For example, over the last 100 years, sometimes even less, okay? And they consider, okay, let's consider, a few hundred data points of floods over the last 50 to 100 years, and they make this plot of discharge during the flood versus how often a flood of that size occurred, okay? And of course, on average, those smaller floods occur more often. But it's important to recognize that this record is incomplete. We're only considering data over a human timescale, which means that we might have missed the very, very large flood events that happen very rarely, okay? So for example, it doesn't mean this 100,000 cubic feet per second flood never happens. It just means it might only happen every 1,000 years, and that we have no record of it happening on a human timescale, okay? So although we're able to do this and we're able to project this relationship up towards larger flood events, we don't really have any data to actually constrain how often those large flood events occur. And of course, these large flood events are the scariest. They're the ones that would do a lot of damage, and in many cases, we don't have a lot of information about how often they occur. But one thing we do know is that humans are probably changing the recurrence interval of floods. And this is another problem with this approach, is that recurrence intervals are built entirely on historic data, on things that happened in the past, okay? But humans are changing hydrologic conditions. So it's unclear if we can really use those past relationships to predict the future. And one example of that is urbanization, which we've already talked about. We know that larger floods will occur more often because the runoff fraction is higher off the impermeable urban areas. So what might that mean? It might mean that your historical record is based on the unurbanized setting, something like this, where, for example, a 2 cubic meter per second flood occurs roughly every 2 years, okay? But now, let's say you've built up 50% urbanization. So we're looking at this line, maybe that 2 cubic meter per second flood now actually occurs every 5 months. So that flood has become much more frequent because of urbanization, but our data may or may not capture that. And another example of the same phenomena is global warming. We've already talked about how global warming may result in more violent storms and causing larger floods to happen more often. So that obviously would also increase the recurrence interval of large floods. There's not a lot of data on this, but here's one plot from the Owl River in Australia, which shows that before 1950, a 2.1 cubic meter per second flood might have occurred about every 2 years, and now, after 1950, that same size flood appears to happen at least every year. So again, we have to be careful using historical data to forecast the future because conditions may have changed. So in summary, we introduced the idea of channels and floodplains. We looked at what a flood hydrograph is and how that data is generated. We looked at what controls the intensity of flooding, including floodplains, runoff fraction, and storm intensity. And then we finished by understanding how geologists document flood recurrence intervals and try to predict how often floods happen. So I'll leave you with a couple concept questions. You'll be able to take these on the quiz. And thanks a lot for listening.